In the last video, we considered continuous one-dimensional dynamical systems, and there we saw how to classify such systems. We saw um, their types of bifurcation, things like saddle node, transcritical, and all that. We also saw applications in population modeling, where we saw things like logistic growth. We also saw early effect, where there's an early threshold that below that threshold the system does not thrive, but above the threshold, then the system can work. And then we also saw harvesting, which is logistic growth with some a portion of the population taken out from time to time. So here we are looking at discrete one-dimensional dynamical systems as opposed to continuous, which we considered the other time. Okay, discrete one-dimensional dynamical systems. It's a bridge between it's a bridge to chaos, right? Like we saw that for for continuous one-dimensional dynamical system with in one dimension there's nothing like chaos in that case for continuous, but for discrete we begin to see some introduction to chaos. So this lesson introduces discrete time nonlinear dynamical systems and explains how simple iteration can lead to chaotic behavior. So the general form of a discrete dynamical system is what you see here. A discrete one-dimensional dynamical system is defined by xn plus 1 equals f of xn. For continuous, right, that'll be x dot or the x dt equals f of x like that. Okay, so here now, xn plus 1 equals f of xn, where xn is the state at step n, then f is a nonlinear map, all right, and then time is discrete. So here we have jumps like we have x naught, x1, x2, so time 0, time 1, time 2, and so on and so forth. So time is discrete. That's why it's a discrete one-dimensional dynamical system. So we study how xn evolves under repeated application of f. So as we continually apply f, so we want to see how the system continues to evolve. And that is the whole essence of dynamical systems. They change, they evolve over time like that. So let's look at iterated maps now. Iterated maps. An iterated map applies a function repeatedly, right? So imagine you have x naught from x naught to x1, you have so if you apply x naught, you get x1. That is x1 is f of x naught, and then to get x2, you have to do f of x1. So when you apply a function repeatedly, you say that's an iterated map. So each application of f generates the next state, as we're going to see a lot in this video. So iterated maps model population growth. It can model economics, it can model neural activity, and even chaos. So a very good example of that would be this. Now consider the map f of x equals 0.5x plus 1. So this is the function, right? But to make it into an iterated map, it becomes like xn plus 1 equals 0.5 xn plus 1. We iterate this map starting from x naught. So basically, you have xn plus 1 equals 0.5 xn plus 1, right? Um, see, you have xn plus 1 equals So that's x sub n plus 1 equals 0.5 xn plus 1 like this. So you start from, you say at n equals 0, right? You have x 0 plus 1, that's x1 is equal to 0.5 x naught plus 1, basically. And then, of course, if you have a value for x naught, you can fix that in. So, I mean, if you had an x naught to start with, you could do that. Then you now go next, you have n equals 1. So at n equals 1, you then have x2, that's x1, n is 1, and 1 plus 1 is 2, equals 0.5 x1 plus 1. So, but don't forget, you already have x1 here. So things can get complicated so fast. So you have 0.5 into x1 is now 0.5 x naught plus 1, which is now like 0.25 x naught plus 1. That's x2. So you can go on and on like that. That's what an iterated map looks like. Okay, so with that in place, then okay, we can do that. We can show the iterated map using Python code. That's an easier way to go, because I mean, if you want to see as many as possible, right? You need to code because if you keep going and going and going, it can get really messy. Like you can already see if I continue like that, now I already have 0.25 x naught. So the next one I'm going to have, in fact, let me even try that next one so you can have an idea what I'm talking about. This is x2, right? So if I now go for n equals 2, what happens? It means that x3 is equal to 0.5 x2 plus 1. And then that means, oh, what did I even do here? I didn't do, now you can see how messy things can easily get. I didn't even do anything as I should. So x2 is 0.5 x1 plus 1. So x1 itself is 0.5 x naught plus this one plus another one, right? So that is 0.25 x naught plus 0.5 plus 1 like this. So that x2 itself is 0.25 x naught plus 1.5. So if I then go for n equals 2, so at n equals 2 now, that means xn plus 1 will be x3. So that will be x3 equals n is 2, right? So we have 0.5 x2, 0.5 x2 plus 1. So x3 now is equal to 0.5 into what is x2? 0.25 x naught plus 1.5 plus 1, So x3 then becomes, if you expand that 25 times, so that's 1.25, 125, that's 0.125 x naught plus 5 times 15. 5 times 5 is 25, 5 times 1. So that's two decimal places, that's 0.75, all right? So that'll be 0.125 x naught plus 0.75, okay, plus 1. So that means x3 is 0.125 x naught plus 1.75. So if you follow the pattern, you can actually come up with this standard formula for it or something like that. So yeah, so you can keep going like that. And that's the idea of an iterated map. So, but with coding, you can go faster. So just write the code once and then you can go as fast as you want to go. So, and that's exactly what we have right here. It's coming up. So here, so if you keep going, see what happens. So but in that case now we take an x naught. If you say okay, x naught is 0, for instance, if you take x naught to be 0, you know if in this case I didn't take x naught to be anything. So if we now take x naught, let x naught be 0, right? So it means x1 will just be 1, easy. x2 x2, I mean, I wouldn't have had to do this plenty thing. So x2 will just be 1.5, okay? And then x3 will be uh 1.75 and so on and so forth. So if you have a number, you won't have to do this complicated well, not so complicated, but at least not, you won't do something you have to do so that much. So you can see 0, 1, 1.5, 1.75, 1.875, 1.9375. So it keeps going and going, and it is moving closer and closer to 2 as you go. So you see the estimated limit is 1.9999 something. That's roughly 2. And that's why if you do the convergence to fixed point now. So the fixed point is 2. So it converges towards that fixed point. Of course, we've not really done fixed point in this case, and that's the next thing we are going to. So you see, so here I didn't have a number. That's why I had to do all those plenty messy calculations. Okay. So talking about fixed point in this case now, how does this work? At fixed point here, a fixed point x star satisfies x star equals f of x star. So once reached, the system remains at x star forever. So once the fixed point is reached, so in the case of continuous like that, right, we equated the right hand side to 0. But in this case now, we just standardize everything left and right to x. So imagine if you look at this, xn plus 1, all right, equals 0.5 x plus 1. So for that x, the same xn plus 1. So you have xn plus 1 equals 0.5 xn plus 1. So for fixed point, right? For fixed point, it just every x just becomes x star, For fixed point, xn plus 1, it means at fixed point, it means all the x's are the same. So x star is just 0.5 x star plus 1. That's what fixed point means in this situation. So that means we have x star minus 0.5 x star equals 1. So 1 minus 0.5 x star is 0.5 x star, and that is equal to 1. So if you divide both sides by 0.5, so or if you like, I mean, one smart way to go, 0.5 is half. So you have half x star equals 1. Multiply through by 2, you have x star to be equal to 2. And then you discover that, when we, in that iteration, you discover that the number was getting closer and closer to 2, as you can see right here. And this estimated limit is that 1.999, which is as good as 2, right? So, but by computation, we discover that that x star is equal to 2 here. So the fixed point x star is simply equal to 2. So for discrete systems, right, at equilibrium point, instead of just equating to 0, you just set, just equilibrium points in discrete system means all the x's are the same, right? So the x's are not changing anyhow you look at it, okay? And we can do a simple code for this. So f is lambda x, 0.5x plus 1, x is equal to 0 for everything in the range up to 30. You can just keep going, and then, and that keeps moving. So you get 1.9999 something. So, and that is the fixed point. But of course, here, this is an analytical way of getting that. So don't forget to find equilibrium points for continuous systems. You equate f of x to 0, which is the right-hand side. You have nothing to do with the x dot or the dx dt. But for discrete system, so if you have anything, like if you are given any x you see, just turn everything to x star. So if you had like xn plus 1 equals 0.5 x raised to power, I mean xn raised to power 2, or I mean minus, say, even xn if you like, right? So all you just need to do is just change everything to any x you see, just change it to x star. So x star is 0.5 x star squared if you like, minus x star, like this. So then you can now work with this whole idea, and then you get what you need to get. So that's how that goes. So for discrete, just freeze all x's, make all the x's the same. But for continuous system, equate the f of x, the right hand side of the x star, x dot or y dot or whatever you're working with, equate it to 0 and solve. Okay. So now let's talk about stability via derivatives. I mean, we've done this a couple of times, but now we are at it here. Stability via derivatives. Let x star be a fixed point. So if x star is a fixed point, then you can compute the absolute value of f prime of x star like that. Then it means if the absolute value of f prime of x star is less than 0, it is stable. If the absolute value of f prime of x star is greater than 1, it is unstable. If the absolute value of f prime of x star is equal to 1, it is marginal. Now you see, in the case of continuous, we did the derivative, right? But that one was straight up. If f prime of x star is less than 0, stable. If it was greater than 0, unstable. But if it was 0, that means you can't determine the stability of that. But for discrete now, the approach is different. The approach here, you take if the absolute value, so you compare it with 1, not 0. So in this case now, you want to find fixed point. You have f of x is 0.5x plus 1. So if you differentiate, you get 0.5. The absolute value of f prime of 2. Now, we already know 2 is the fixed point now. So, but interestingly, the derivative has nothing to do with 2. So whatever it is, the absolute value of f prime of 2 is 0, is absolute value of 0.5, which is less than 1. So, and because of that, so we can say the fixed point is stable in this case because 0.5 is less than 1 for a discrete case. Now, let's look at periodic orbits. A point has period k if the kth derivative of f of x is equal to x, then you say it has period k. But if the mth derivative of x is not equal to x, but then the mth derivative of x is not equal to x for any m that is less than k, okay? So you don't have any case, right, where the derivative less than k is actually so for any value less than k, the derivative does not ever give you x. So examples, k is equal to 1 is fixed point, k equals to is periodic orbit, and k equals 4 is periodic. So if k equals 1 is a fixed point, that's the deal here. Then k is equal to 2 can actually be the period 2 orbit, and k equals 4 is the period 4 orbit, like that. Okay. So we take an example right here. So using a logistic map like we've always done, Rx into 1 minus x. That's a popular that in fact that's about the most popular equation we've seen since we started this playlist on dynamical systems. So that's what we are working at, and then we just want to so we want to do the whole thing. We take R to be 3.2. This 3.2 is carefully chosen because if you pick something else, you won't get the picture, the kind of picture you want. But of course, you can always play with that to see what happens. And then we get the logistic map. We take the initial condition to be 0.2, which you can always change as you like, just to explore what happens. So with this now, we have last values of orbit. We have 0.5130 all the way to 0.799, blah, blah. So here we did two periods are detected, right? So you see, after you have this, you keep going. After sometimes it comes back. After this, it goes back to this. So you have two periods basically. So if you have after each layer, now you can see this number after one, two, one. So one, two, one, two, one, two, one, two. So if you have three different last values of orbit, then you'd have said that the period was one, it was three, but here it's two because after so you have this value, another value, then you come back to the value again. So how many values do you count before you come back to the same value? That's the number of orbits. So 0.513 something something, 0.799, 0.513. So after two, you come back to it. So the period detected is two. Now we have the cobweb diagrams. Okay, cobweb diagrams are very popular in discrete systems. So cobweb diagrams visualize iteration. And what we do basically here is it plots y equals f of x, right? And then it also plots y equals x. And then you move vertically to f of x. So you move horizontally to y equals x and repeat like that. Okay. And they show convergence, cycles, and chaos. So this is what we just see down here with this Python code. So we see the cobweb diagrams. So it's more like let me do a rough thing before I show the Python code. So you have something like this. So maybe you plot your function, whatever the function is, and then after that, you now plot y equals x. You know, y equals x is this straight line that passes through the origin. So the cobweb thing, you now keep climbing, you move across this line or something. I mean, that's just a rough idea. So let's show the real thing, using Python. So I click on this now and the code is run. So you can look at the code. You want to look at the code. So in this case now, the function is what you have in blue. So the function f of x is what you have in blue, and then y of x is this orange one. So the climbing I told you about. So each step you go one, okay, you go next, climb. So you keep going because until you so now look at this. You go up to the function f of x. Then from there you move to the next step. You go to the function. Next, you go the next step to the line. So you see, you come to the peak and then you come out like this. So from here, you come down, then you come here. So you see that you get trapped in this kind of cycle right here. So, and that tells you that's the equilibrium is around that portion like that. So this cobweb diagram for R is 3.1, X naught is 0.2 as we have here. So that's the idea of cobweb. I think it's some people call it cobwebbing. There's a cobweb diagram. So that helps you, like we said, to see convergence, cycles, and chaos. So in this case now, it looks like we have a kind of cycle coming here because now if you pick a point from here, we start from 0.2. So 0.2, you go to this at y equals x, then you go to the function. All right, from there, you go to the line again, then you go to the function. From there, you go to the line again. Then you go back to the function. You go to the y equals x line, I mean. Then you go back to the function. So it's more like you are trapped in a cycle, and that looks like a triangle here, right? Or is it rectangle? Square rather, square. Then we have logistic map. Okay, so the logistic map is given as xn plus 1 equals rx into 1 minus x. Of course, if you want to find the fixed points, everything will just be x equals rx into 1 minus x. So if you solve for x in that case, you get the fixed point. So where r is a control parameter in this case, so this r is a control parameter, and xn has to lie between 0 and 1. right? So it's this models population growth with limited resources, and that's why it's logistic, because it grows and then it stabilizes at a point. Because maybe in the case of ecology, there's a carrying capacity beyond which the system cannot grow, right? So it saturates at that point. And then here we have the behavior by parameter R. If R lies between 0 and 1, it leads to extinction of the system. If R lies between 1 and 3, we have stability. If R lies between 3 and 3.545, we have period 2. That means we have two possible existence. And if R lies between 3.45 and 3.57, we have doubling. Like, we have a kind of branching out, some kind of chain reaction, if you like. And then if R is greater than 3.57, we have chaos. Okay. So we want to play with all these possible values of R to see what happens. So uh, first, R lies between 0 and R. In this case, we have the logistic R X naught this, and then you now do this X logistic 3.9 0.2 200. So if I run this now, okay, we have, so 3.9, by the way, 3.9 is 3.9 is big. R is bigger than 3.57. So 3.9 leads to chaos. So you can see the logistic time series is very chaotic in this case. That's chaos. That's for 3.9, which actually lies between, which is bigger than 3.57. What if I choose some 3.5? 3.5 is between 3.55 and 3.57. So I make this 3.5. In that case, we expect it to be doubling, right? So if I do 3.5, so you have doubling happening like this. That's for 3.5. Then that's doubling. Then what if it's from 3 to 3.45? So let's say I choose 3.1. Okay. If I choose 3.1, that'll be period 2. 3.1. So for 3.1, I run that now. 3.1 gives period 2. Then apart from that, right? If I do from 1 to let me choose 2 now. That will give us stability. 2 gives stability, so I go for 2 now. So I run that. So we have, that gives stability. So everything just saturates and stays somewhere. That is stability. Then 0 less than R, I mean, maybe 0.5 now. That leads to extinction. Okay, that leads to extinction if we have something between 0 and 1. Okay, so you see everything just dies out like this. So these values will determine what really happens. So let me take you back to 3.9 where we have chaos. So you have all the possibilities in this case, depending on whatever value of R you choose, like that. So that's the population growth rate in this case. So you already know what to do if you want to keep, if you don't want chaos, whatever you choose, just fix the value of R. So for 3.9 now, which is beyond 3.57, you have a chaotic logistic map like this. So let's talk about period doubling cascade. Period doubling cascade, it's one phenomenon in discrete systems that is worthy of attention. So the period doubling cascade, as R increases, imagine from 1 to 2 to 4 to 8. So from 1 doubles to 2, 4, 8, 16, and it goes to infinity. This sequence accumulates at the onset of chaos. So we have this sequence accumulating at the onset of chaos. This route is called the period doubling cascade. So this is called the period doubling cascade. So if you check that out on a logistic map, so you see you have Rx into 1 minus x, same map, but now we are collecting all the points, and then as it's going, so we have x is 0.5 for starters, and then so we want to collect all the points. So in this case now, and then we're taking it between 2.5 and 4.0 in 5,000 steps, and then we run all this now, then you see what happens. So because we're talking about period doubling cascade, so see what happens. Things happen so fast. So you have the points going. At this point, it becomes like pitchfork bifurcation. And beyond, as you keep going, you have the doubling getting faster and faster. Here we have it's slow, then here it's fast, a bit faster. Then from there it's faster. And before you know it, the whole thing becomes very chaotic. And that is the idea of period doubling cascade. So it happens so fast. And then that takes us to the idea of the Feigenbaum constants. So if the growth rate R sub n let Rn be parameter values where doubling occurs. So if doubling occurs like what we have up there, so you define that delta sub n is equal to Rn minus 1 all over Rn plus 1 minus Rn. So then if you do this, delta n approaches delta, which is approximately 4.6692. So this 4.6692 is what is called the Feigenbaum constant. So the meaning of the Feigenbaum constant is this. It appears in many nonlinear maps, and it is independent of system details and shows universality of chaos. So chaos follows universal scaling laws, basically. So that's what the Feigenbaum constant tells us. So we go for symbolic dynamics. Now, this is another interesting concept. Symbolic dynamics converts trajectories into symbol sequences. So the partition is this. We have the closed interval 0 to 1, which is A union B now. So imagine this example. If x is less than 0.5, it goes to 0. If x is greater than or equal to 0.5, it goes to 1. So we have two possibilities of existence, that's 0 and 1. And then the trajectory becomes a binary string. So if you do symbolic dynamics now using Python code, same logistic map, Rx into 1 minus x, but then we are generating the orbit. So generate orbit, you have the function f, and then you have an initial condition. You want to equals 200 and n is 100. Then you set x to x naught to start with, and then you go by the time you declare all the codes, then R is 3 and that's chaos, and X naught is 0.2, the initial condition. Then you declare the logistic, you do the orbit, you declare the symbol of the orbit. So like any case you have 0.5, less than 0.5, you have 0, greater than or equal to 0.5, you have 1. So if you do that, if you accumulate all those points, it gives you what you call the symbolic dynamics. You have the symbolic code, and this is what that leads to. So you see, you have see all these things now. So here now, 1, it means you had got R to be greater than or equal to 0.5. 0, you had got R to be less than 0.5, and that keeps going like that. So and then we then have this logistic map of it with symbolic partition like this. So you have the frequency 0, 0.371, and 0.6. So you have all of that crazy dynamic going on there, as far as symbolic dynamics are concerned. So here you are translating trajectories into symbol sequences like that. Okay, so what's the interpretation of all of that? So first of all, you have periodic motion. Periodic motion means repeated symbols. Okay, repeating symbols. And chaotic motion means random like symbols, and this enables entropy and information analysis. So symbolic dynamics links chaos and coding theory. So symbolic dynamics can help us link chaos and coding theory like that, because it translates growth rate into sequences of zeros and ones, with r less than 0.5 giving 0, and r greater than or equal to 0.5 giving 1. So in summary, when we talk about iteration, the role of iteration is to show the dynamics. Then when we talk about fixed points, we talk about equilibria in this case. For stability, stability talks about predictability. Then we have periodic orbits, which shows us the structure of the system. Cobwebs are for visualization. Logistic map is the canonical model. So you see that everything we did, we kept using R into 1 minus X, right? Uh, yeah, Rx into 1 minus X exactly. Then logistic, we have doubling. Doubling is the root to chaos. So if doubling happens, growth is good, right? But if growth becomes too fast, it can become a problem. And that's why we have issues like cancer and everything. So because cells, good cells, normal cells, I mean, you have cells and then they begin to grow too fast, and that becomes a problem, right? That's why cancer is chaotic. So, but when cells grow normally, you have a stable system. Then you have the Feigenbaum, which talks about universality, universality of chaos, so to speak. Then you have symbolic dynamics, which can give us it plays the role of giving us information, because it talks about some kind of entropy, which is very good in information theory. So in this case now we see how order can become instability, and how instability can degenerate into chaos. So we have some practice problems. I guess I can show them in twos if possible. Yeah, I think that's possible. All right. So Iteration, let f of x be 0.4x plus 2. Start with x not equals 0. Compute x1, x2, x3, x4. That's easy. So you just say this is xn plus 1. Should I do that? I don't know. I did something like that already. So xn plus 1 equals 0.4 xn plus 1, I mean plus 2. At x equals 0, you have x1 equals 0.4 x naught plus 2, and x is supposed to be 0. So you just have 2, and then you keep going like that. Then, of course, you can write a Python program to take it. So with a Python program, you can go as fast, you can even go to 1,000 steps fast. Then for fixed point now, find all fixed points of this. So to find all the fixed points of this now, all you just need to do is you just say x is equal to x star is equal to x star squared is equal to minus 3x star plus 2. And you solve for x there, and you're good to go. Then, so yes, I mean, this is, yeah, doing this is more like solving for, yeah, and that's the idea of fixed point, right? They all say x is equal to all that, and then you solve, and you're good to go. Then verify numerically that the fixed points are correct. Then text convergence from different initial values. Okay. Then 3 and 4 now, we have stability analysis. For the map f of x equals 2x into 1 minus x, find all fixed points. I mean, just say x is equal to 2x into 1 minus x and solve for x. You find all the fixed points. Then you can compute f prime of x. So those fixed points you find now, then you can differentiate this f of x and then substitute and see if the absolute value is less than 1, that's stability. If it is greater than 1, that's instability and all that. Then you have logistic map like this. X naught is this, plot xn for this for 200, so you can easily find that. So as you vary these values, just like you saw before, you can have 3.9, of course, is going to be chaotic. 3.2 should be doubling based on the partitioning we saw the other time. And for 5.6, you have periodic orbits. You can try, I mean, this is another one for cobweb diagram. So you can just use the same Python code to do this. 7 and 8, we also talk about Fiberman ratio. So you want to show that delta n approaches 4.669. So as you compute this, so let R1, R2, Rn be successive doubling values like that, and then you can compute all of this. Then 9 and 10, finally, you have symbolic dynamics, which converts code, which converts what's that thing now? It converts, oh, we saw the concept. I don't know why I just, yeah. Symbolic dynamics, it links chaos to coding theory exactly. So chaos is linked to coding theory. So you have symbolic dynamics. So you can just use the same code to try all of this. And then sensitivity to initial conditions, you want to check all of this. So with this, I come to the end of this interesting video about discrete one-dimensional dynamics. Let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. If you have subscribed to this channel already, I must thank you very much for doing that. If you have not, you don't want to keep missing out on these great things I'm sharing here, why not go ahead and subscribe right away and hit the notification bell so you can always get alerted each time a new video is released. All right. Having done that, you can also become a member of this channel by clicking on join, and that gives you some special privileges like access to the PDF, some of the PDF copies of the notes I use for these teachings, or some other perks you're going to find as you click on join. All right. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.